So in the last segment we were seeing in fact just as a small yeah, I'll write from here. So just to put the things in perspective, there was a sphere and it was trying to radiate some acoustic energy. That is how we defined the source, which is in contact with the medium, and it can transfer energy. So this space or this region in space is capable of transferring energy, and we said that because it's spherically symmetric, so theta and phi dependencies are not there. So then from there we said that the pressure which it will produce will be obviously a function of only r and t, and then we wrote the spherical Laplacian form, and from there we came down to this equation. Sorry, right. So this we came up to, and then we said that so this is the normal wave equation with suppose this y as a function. So we know the solution of this. From there we figured out that okay, our solution will be something like say, what do I write? 1 over r f1 ct minus r plus 1 by r f2 ct plus r, and so this r basically is coming from this fact, because rp if you multiply, so this is the general formula or general form of solution. Now we said that this we won't bother about because this is a converging type of wave, and we are more interested in now the radiation thing. So this is what our solution is. Okay, and please note that here we are using the general form like this. We are not using omega t minus kr. We could have used it, but why are we not using that omega t minus kr? Because till now whatever we are discussing, they are general. This function could be anything. So omega t when we are using, that means we are actually talking about sinusoidal oscillations. Okay. Now up to this point we are completely general. This function could be any function of time. Okay. Now so yeah, in fact from there we went into the discussion that this 1 by r is the cause for getting the amplitude reduced. As you increase r, the amplitude of the pressure goes on decreasing. Okay. So that's what, you know, the shape remains same but the size gets decreased. So that's the difference from the plane wave. So that's where we and then what we can do is see, we had this rho naught del u r over del t is gradient of this. Now because again we are in a situation where you can think of this as a 1D, because only the radius or radial direction is the coordinate in which things are varying. So it almost again looks like a 1D equation relating the velocity and the pressure. And now that if you think that P is some, I am writing capital P Ct minus R over R. Okay. So this is what that means. Why we are writing like this is, there is some function which we are trying to evaluate now from the the boundary condition at the surface of this sphere. So that's our objective now. Okay. So what happens is at r is equal to a, because if the radius of that sphere is some a value, so then this can be, we will see now that this can be evaluated from the condition at that location. Okay. Then you can predict p just by multiplying this 1 over r factor. Okay, because this shape will be decided at the source. Okay, depending on, because anything that is getting generated there is just going out, there is nothing coming back, it is like the completely radiated condition. So the shape to the pressure wave is given at the source itself, and then it gets diminished with this function. So that is what we are trying to now do, to see that okay, how that p, it depends on what type of things. Okay. Now this gradient, from here what you can do is you can derive this to be over dr. You can do that on your own also and just check that, just I am differentiating this with respect to r to calculate this, which is equal to dt, right. So I just substituted this here, nothing else. Now what you can do here is, just we will define one more parameter in a way which is generally defined to express any small sources. So what I'll do, suppose you have 4 pi a square times u is the velocity at that surface. And now that if you define as say s as a function of time, so here also I can write as t. Okay. Now this I'll say at r is equal to a. So what does it give you? This is the velocity of the surface, this is the area of the sphere. So basically it is giving you volume flow rate, right. So this is meter per second, this is meter square, so meter cubes per second. So this s as a function of t now, and then this is not a function of r at this condition, because on the surface you are talking about. Okay. So this is just a function of time. So this will give you the, it is called the strength of the source, how much volume flow rate it is capable of producing, meter cubes per second. And then now here let's say this expression we write it at r is equal to a. So 1 over r dp over dr plus p over r square, but we are suppose talking everything about at that location on the at the surface. So this will be what, rho naught, this will be 1 over 4 pi a square ds over dt, right. Because s is a function only of time, not of distance, so this can be a total derivative also, does not matter. Now if we are talking about say small sources, okay, that means the size of the source is very small, that means this r is very small, okay, then this r square is a much faster rising function than r. So that means this will be the dominant term, okay. So that means you will have um, P will be equal to so this r square and this a square will get cancelled at r is equal to a. Yeah, anything?
So there should be a minus.
Here?
Yes, sir.
Are you sure? Because there is a minus over there. Because, yeah, got it, right? This should be positive. Okay. So, what I was saying? Yeah. So, this term is the dominant term. So, this is not there anymore and you are evaluating r at a. So, this r square a square gets cancelled. So, basically you are, I need some space here. So, you are basically writing something like P is equal to rho naught over 4 pi ds over dt, right. Now, what does it tell you? Means this is the equation. What is that? What this equation tells you? It is telling you that if you have a source, small source, so the small has been taken care of while going from this to this. And if you have a small source for which if you know, suppose the velocity, and all this velocity is very important to know that all the points of the surface, they are moving in phase. That's very important. So that's what this equation is representing. Okay, because this is just a function of time, physically converts into the meaning of they are in phase. If it is a function of r theta phi, they will not be in phase. So the sound field will be completely different. Now, if the surface velocities are in phase and the source strength is s meter cube per second, then whatever may be that function, you just take its derivative and that will give you the shape of the pressure which you are talking about. Remember, we said that first we will think about the shape of the pressure, the size will come later on. Okay. Now, when I say shape, I also mean the initial size included, because this 1 over r will be at different locations. Okay. Now, when I am saying this shape, the initial point, whatever the pressure also will be there, that amplitude will be derived from this only, this part. So, initial point, shape and size is decided by the function of the source, this thing, and after that you can simply write, as rho naught over 4 pi r ds over dt. Now, here I'll write in a slightly different way, not in this form. I'll write in this way. This is a prime, and here I'll write this like this. Just think about it. What exactly does it tell you? I got the shape and size of the wave, pressure wave, at the surface of the source. Okay. Now, first thing, if I go away from the source to a radius r, it will become over r, right. So, this term has come, but at the surface it was just a function of t, but when we go away, the wave will take some time to reach there. So, that means this r over c, you remember I had told you that if you have a function f of t, then f of t minus x over c will be the moving wave, because you can think of this as, how do I call, suppose t is say 10 seconds, you are asking at 10 seconds what is my pressure at a distance of say 5 meters, r is 5 meters, time is 10 seconds. Now what this equation tells you, that to travel 5 meters, wave must have taken this much time, r over c, is it right? Dimension, distance over speed is time, yeah. So this much time it would have taken. Now I'll go back to see what was the time derivative of s at that time, because that would have created the amplitude, right? And now, so that gives me this p at r, and then this 1 over r is the reduction in the amplitudes. Is it clear? From this, can you write this? Achha, this s prime is like this s differentiated with respect to its argument, okay, whatever its argument is, and then in place of that argument you put r t minus r over c, okay. Now if that is so, can you prove that if you have a source which is constantly increasing, it will not create a continuous sound?
Constantly increasing in size.
Because you see this, now what does that mean? It means that at t is equal to 0, the sphere started expanding. This is the meaning, right? Suppose I call this s of t. S of t is constant. That means velocity is constant of the surface. That means the sphere is getting bigger and bigger uniformly at a constant rate. Okay. So this represents a small source whose surface is increasing, or the radius is increasing uniformly with respect to time. Now if that is the form of s of t, what will be the form of ds by dt? No, it is just a pulse, a Dirac delta, because here there is a jump. At t equal to 0, it is not, it is not from minus infinity to plus infinity, it is at 0. So that means its differentiation will be a Dirac delta. So that means now your d s over dt will become delta of t, and in place of t you will substitute now t minus r over c, right? R over c, to get at any location, because see that means a pulse of pressure got generated at the surface at t equal to 0. This is the meaning of that, right? So this ds by dt is delta, if you see here, and this is the factor of which I was saying no, the magnitude. So this is the magnitude of that delta function. So that gets generated at t equal to 0. But then it will take r over c time to reach any point which is at a distance r. So that is what we are representing by this. I am not writing the, okay, I'll write even the, this was rho naught over 4 pi. So here in fact rho naught over 4 pi, but again this is the delayed version of the wave, but then diminished version of the wave will be like this. delayed and diminished. So that means if you are farther and farther away, you will hear less intensity of sound, but for a while. Tuck. See, it is in, but your source is constantly increasing in size. You are seeing that? But you are not hearing a sound constantly. You are hearing just a pulse at any location once only. So that's the meaning. So this is an example where you should be able to understand what this actually means. Okay. Mm-hmm.
So no matter how much no matter the rate at which it increases, you will hear a sound pull up and impulse. Basically, we are fixing u of t right now, right?
We are fixing, yes. Uh-huh.
So we are saying that if basically the source is increasing in its size,
You are talking about whatever may be the velocity?
like
Yes.
there should be a limit.
Okay. All limits are with respect to so many things. Means you are not creating such a velocity where shock is generated. Obviously. Right? Means things are small. Perturbations are small. That's why the velocity also will be small. You can't go into velocities which are compared with c. You can't. Then even much below that you have to be. Yeah. So these are all. You remember, from the fact that we use this, it's a good question to visualize. You remember we had 3 levels of even smallness, and we neglected the second order and third order smallnesses, and we kept only first order smallness, and from where we are discussing everything, and then we talked about it is small again. So there are so many emphasis on small. Okay, so that's why to certain values of velocity, yes, it's independent of the velocity. Till the time you are comfortably within the safe limit of all those approximations, yes, it is independent of the velocity. Okay. I mean, independent of the velocity means what? Means
Not magnitude wise, but at least behavior.
yeah, because see, if I didn't draw the, I never put anything here, right? So if you put number, so I always imagine that it's a unit step function. So that's why I put it delta. If I don't put unit step, it won't be, right? There will be a value here. So in that sense, you can think of. Okay. So if you increase that, obviously a larger pulse will come and larger sound will be visible, audible, but then it's only once. Okay. So, okay, we will stop for this segment now. We will see the harmonic oscillations in the next segment.